Hi, good morning. So I'm here to talk about what's new in Java 8. I'm Maurice Naftalin. I'll introduce myself in a moment. First of all, I would like to say thank you very much to the organisers of JPoint for inviting me here to talk to you today. Thank you very much for coming to here. And to ask you, I don't normally ask for interruptions in a talk as big as this, but the one interruption I would ask you to make is if I start to speak too quickly, or if you're having difficulty in following my English, that's something that I do need to hear about. So are we back on? Just about. Oh dear. Yeah, I get a lot of technical problems. We're down to one now. I had every time I've talked recently, on every single occasion, there's been some technical hitch. So one time I rebooted my machine just before a talk, and when it came back up, I just couldn't find the talk anywhere on the machine. So the next time I didn't do that, and the moment I started, the machine froze completely. So this time we're down. It looks like we're down to one screen. That's a bit of a problem. Can you guys see that? Okay. Right. That's not good. I don't think that's going to work. Have we any way of reviving it? This isn't me anymore. These two screens are not. Okay. Cool. Okay, so I'm Maurice Naftalin. If you have heard of me at all, then it probably is in connection with this book, the book on Java generics and collections, of which I'm the co-author. I'm always very proud to say that this is definitely the best book there is on Java generics. And then I have to add, in honesty, that it's the only one. So just now, I'm involved in a couple of new projects. One of them I started a few months ago, and this is the Lambda FAQ, which I intended as a website that was going to be the sort of reference point for all the questions that people would want to ask about Lambdas as they become more popular and more widely used, and there's more interest in them. And I'm pleased to say that the Oracle team, the Oracle language team, have been very helpful in making sure that the material on there is of good quality. But only halfway, before I really got stuck into that properly, I got another project which came out of that, which is a book that I'm writing for Oracle Press on Lambdas, intended to ship in September 2013 to coincide with the launch of Java 8 and with Java 1. So I felt when I made this slide up, putting under the date of 2013, I felt like putting something like, yeah, right. Because anybody who's written a book will know that projected dates and actual ones tend to be rather different. So today here I'm going to talk about what's new in Java 8, and I've decided to, I've broken the talk down into three unequal parts. So I went a little while ago to a talk about the new features in Java 8, and the talk was entitled, I think, 53 features coming in Java 8, and they were crammed into 45 minutes. And to be honest, I felt like this wasn't the most inspiring. It was very informative, but it probably wasn't the most inspiring talk you could go to, because what happens in a talk like that is that you hear about a feature for half a minute, and then you hear about another feature for half a minute, and then you hear about a third feature for half a minute. So I decided instead to talk just about a few of the specialized changes. I don't call them small changes, because some of these have involved a huge amount of work, but they won't have wide impact. And I've just chosen a half a dozen of those because I'm interested in them. And then I'm going to talk about two medium impact changes, which are the date-time API and type annotations. And I'm only going to spend a few slides on those. And then I'm going to talk about the big picture change, and I'm sure you know what that's going to be. So for the specialized changes, I've just chosen a few pretty much at random, to be honest. Some things that are that struck me as interesting. So for example, if you're interested in the Java ME, then you might be interested in the compact profiles. You might be interested in compact profiles anyway, if what you want to do is, for example, to embed a JRE with a product for downloading. This is finally they've got around to organizing the libraries into the library classes into a more logically nested way. So there's a core profile which has the absolute minimum that you need in order to be able to get off the ground, and then you've got the second profile. There's three. I can't remember if they have names. The second one adds on XML and RMI and JDBC onto the core profile, and the third one adds on JNDI and JMX. So you might, for a lot of applications, get away with just the core profile. So people who don't need, for example, the huge swing libraries and don't need Java FX don't any longer need to have them. Of course, this is not a substitute for Project Jigsaw, for the real modularization of Java, which is a much more elaborate and ambitious exercise. But as you probably know, that couldn't be fitted into Java 8, and that's going to be coming in Java 9 now. But compact profiles take you some distance towards that. So the second one I chose was the Naftalin JavaScript engine. The JavaScript implementation in the JDK is pretty antiquated and not any longer of high quality. Nowadays, there are instructions available in the JVM, like invoke dynamic, more than anything else, which actually allows for much more efficient implementation of JavaScript. So Naftalin is a complete rewrite of the JavaScript engine, and if you're interested in using JavaScript from inside of the JDK, then that's going to be very interesting to you. A third one that I chose, that I hesitate to talk about because Alexei Shipilov is here at the conference today, and he knows, and he's actually implementing this, is a way of signifying cache contention for specified fields. If a particular field is highly contended, then it's going to be evicted from the processor cache very frequently. And since processor cache is organized in what's called cache lines, when any value is evicted from a cache line, then all the values in that cache line are evicted as well. And if there's accidental sharing of the cache line between unrelated variables, then you may actually find that values are being evicted from the cache unnecessarily, and this can really hurt performance. So if we could tell the JVM which are going to be contended fields that will need frequently to be evicted from the cache, then the JVM can give them a cache line of their own. So there's going to be an annotation for that. And if you find Alexei, I don't think he's talking about that today, but if you find Alexei, he can tell you all about that because he's the guy who's actually putting it there. Okay, so a couple more specialized changes. There are updates, as always, to the concurrency library because that's always a very active group. We're going to get scalable, updatable variables, which will work much better under contention than atomic variables. That'll be a big improvement. There's going to be improvements to the concurrent hash map implementation, some new operations added, and possibly an improvement to the API. There's going to be improvements to fork join pool, which is now becoming the implementation of preference for multi-threading. A few others at random. I put the next two in because they're actually quite controversial. Removing the permanent generation from the hotspot JVM will be seen by many people as a good thing, especially if you've actually struggled with hot swapping classes in development using an application server when out-of-memory errors in the permanent generation just become a real pain. But on the other hand, we're probably going to lose some diagnostics there that were very useful, and we're probably no longer going to detect. It's going to be harder to detect memory leaks in static data. They're retiring some rarely used GC combinations, of which the one that you might actually notice, but I've certainly had a reaction from a lot of people I've talked to about this. It's incremental CMS, which was a mode that actually did have quite a lot of interest. Anyway, that's going, and some other things are going now. G1 is coming in, of course, as the garbage collector. That's where the focus really is. Okay, one last one. the Java doc is being exposed to programmers. So there's going to be an API for exploring the data structure that Java doc uses, the doc tree, and it's going to be possible to access that from inside javax.tools. Okay, so I think there I've probably talked about 7, and there's probably about another 43 which you could go and look up in the appropriate JEP, and those are all going to be coming. And some of them I may well have missed out ones that will be of particular interest to you, but I can't tell what's particularly interesting to you. Okay, so that's all I'm going to talk about, the small changes. The medium impact changes are the date and time API and type annotations. And when I'm talking about the date and time API, I just couldn't resist, though it's a little bit off topic, I could not resist putting this slide up. So here's a picture of 2 guys with guns, and the question is, it's a little pop quiz, who are these guys and why aren't they Russian? And has anybody heard of this? Does anybody know what I'm talking about here? In Russia, I just can't resist talking about this. Okay, so if you look at the top right-hand corner of that slide, you see very faintly there's an Olympic logo. So actually, these 2 guys are the gold and silver medalists, respectively, in the single trap shooting event in the 1908 Olympics. So they're Canadian. They aren't Russian. In fact, if you look at the list of nations competing in the shooting events in the 1908 Olympics, this is what it looks like. Well, this should be what it looks like. If I can get this to work. Oh, great. Sorry, excuse me. Sorry, I have a crash. I'm cursed. This is definitely not my day. Let's see what we can do. Okay, keynote. Come back, keynote. Keynote. Okay, let's try it again. Who are these guys? Who are these guys? Okay, so looking at the participating nations, you see that prominent by its absence is Russia. You would have thought, or I would have thought, that if there was one event, no, sorry, I shouldn't say that, but I would have thought Russians would have known something about shooting. So the reason that the Russians don't appear in this list is not that they didn't want to take part, and it wasn't that they didn't turn out for the 1908 Olympics. The problem is that they arrived in England, where the shooting event was being held, just as everyone else was packing up to leave, because they timed their arrival according to the Julian calendar, and the Gregorian calendar was 2 weeks ahead of them. So this is why the Russian shooting team never took any part in the 1908 Olympics. And
but you still have Russian flag.
You have the Russian flag.
I've really gone in dangerous territory here, haven't I? So the history of the Java date and time APIs, there's really 3 that are worth paying attention to. There's the original one that came in Java JDK 1.0, which is Java util date and Java util calendar. And these are just absolutely terrible APIs to work with. I put them up as the strong contenders for the all-time worst platform library design. But actually, I don't think there is any contention. I mean, I certainly don't know of anything that's worse. So a long time ago, those were not replaced, they were supplemented by the JodaTime library, which was a product of a single developer, in fact. It's really a grassroots thing. A friend of mine called Stephen Colborn, who produced this very high quality date-time library, JodaTime, which has been very widely in use for a long time. But it was never adopted into the JDK, mainly because Stephen is a perfectionist, and he knew from experience that he'd made some mistakes, there are some fundamental mistakes in the design of JodaTime. Not that it isn't a very usable library, but he's a guy who wants to get things right. So JSR 3.10 is the result of years of work to re-implement JodaTime without the problems. So if you're programming with dates and times, then you'll probably recognize that the goals and the design principles I'm putting up here will really be a big improvement on anything that you've seen before. If you haven't used JodaTime. If you've not been programming with dates and times, then you will find it really hard to imagine just how primitive the platform library capabilities have been until now. So the idea of JSR 3.10 is to provide a comprehensive model for date and time using global calendars, but it's strongly oriented towards the ISO standard that represents the Gregorian calendar. Immutability is a really strong theme. Almost all of the objects in this library are immutable and therefore thread safe. And needless to say, they're type safe. So the enums are very heavily used. And the design principles are that, as I say, that it should be immutable. Also, that in general, the API is designed to be fluent. Is this us? All right. It's this one. Is it okay? It's. For the moment, okay, right. The API is designed to be fluent in a way that you'll be used to with domain-specific languages. So you can see here that you're meant to be able to read it in a way that's actually quite close to the developer's intentions. The of method is a factory method here. We're going to create a local date out of those arguments. We're going to replace the year field in it with year. With year, and then we'll replace the month field in it. And each one of these replacements will create a new object. So immutability is this very strong thing. The underlying design principle is that there are two basic concepts of time when we're imagining writing programs. One of them is a continuous time scale suitable that machines essentially work on. So if you calculated the time as a machine sees it, then you're seeing it in terms of milliseconds since the epoch, or as it's going to be now in JSR 3.10, nanoseconds since the epoch. So it's a single incrementing number. And that the 310 class that represents that is an instant, and this is nanoseconds from the 1st of January 1970. And working with that, we can see that it's quite a fluent and flexible API. So you can say here we're saying that a start instant has been constructed here from so many milliseconds past the epoch, and then the end instant is at the moment that the program's executed. And we can say things like start is before end, and we can say things like end is after start. We can construct a duration out of seconds, or we can construct it out of a time unit. We can add durations together. You can add durations to instants, and so on. So it's really kind of quite flexible, and works in terms of the sort of concept that you might come along with when you first started programming with this. It's very much in contrast to the Java util classes. Time for humans is field-based. We think in terms of hours and minutes and seconds. In terms of for duration, we do it. In fact, it's not called a duration. It's called a period. You talk about a period of 3 hours. A duration is a length of time, but a period is 3 hours. And there's a big difference if there's a leap second in the way, or if there's a daylight saving time shift. 2 days is the period of 2 days is different depending on whether there's a daylight saving shift during that period. The duration is quite variable. So that's how humans think. So there's a complicated interchange going on between those. I just put in some random sample code to show the kind of thing we would do. Here I'm building a local date, then I'm building a local date time. A local date and a local date time are dates and date times without time zone information. They're okay for a single locale, but not for anything else. So a zone date time now incorporates, that's been created from a local date time here, I should say LDT, sorry, and a zone ID. So we've taken a local date time and we've fixed it in Europe stroke London or wherever. And then we can do arithmetic on date times as well. Here we're subtracting 12 hours from it. So you get the kind of idea. It's really very fluent and responsive API. There are other features that I won't spend a lot of time on. You can ask how long it is between two events. So that's actually something that's usually very hard to do with datetime APIs. There's integration with the Java util classes. The Java util classes have been retrofitted with conversion into 3.10. But not the other way around, because the hope is that the Java util classes will die out. There's database integration has been thought about. There are regional calendars for some areas like Japan and Thailand, where the Gregorian calendar is not in normal use. You can get the current time, and you can set the time for dependency injection testing. So you can say I want to fix Joda time at such and such a point. And then you can repeat a test over and over again, obviously. And there's extensive formatting and parsing capabilities built in. So really, finally, at last, Java has got a competent datetime API. If you've been programming, you can tell from my sense of aggrievement that the lack of a datetime API has been a pain for me personally. If you've been working in that area, then you'll feel the same way. If not, you'll be wondering, what on earth am I talking about? Okay, the second medium-sized change is type annotations. So I'm going to talk about these very briefly, because there's a talk this afternoon that Alexander Ilyin is giving, and he's going to go into it in much more detail and with much more knowledgeably than I am. So you know that annotations currently are a kind of metadata that can be attached to declarations. And that's been the case ever since they were invented. And here I've taken some JPA annotations and attached them to the declarations of a class and to the declaration of a method. But they've not been able to be used anywhere else until now. The reason that we have these annotations, of course, is so that tools can derive more information about a program than simply the source code gives. We can give extra information that they can use either at compile time. They're either embedded in the source, or they can be embedded in the class files, or they can actually, if you specify the right kind of retention policy, then the JVM will preserve them after the classes have been loaded. So type annotations, type annotations now allow annotations to be applied to the use of types. So that means almost everywhere where types occur in practice. So I've got some examples here. I'm saying that my object here, I've annotated the type of my object there to say this thing can be interned, and a tool could therefore see that it's okay to use the equality operator, double equals, because interned objects that's okay to do, and a check could therefore be made. You can imagine a tool that was checking for false uses of the equality operator would be able to see that using this annotation that it was okay to use the equality operator there. So the declaration of the attachment of an annotation to the type in the cast on the next line to say the string must be non-null is kind of self-explanatory. Again, a tool would use that for analysis, and so also with the third one as well. So there's a few places where you can't use these, where you can't attach annotations to types, where the type is not actually being used. So, for example, with class literals, it wouldn't really make much sense to do that. Import statements and so on. And the information that's attached to these types is only available for use at compile time, because of course Java doesn't retain any information about the type with which a variable was the type of a variable that is being used to refer to a value. So these are compile time only, but they do supply a lot of power to new tools. So the idea is that this is actually really going to set the annotation system free to be much more flexible, and static analysis tools can be much more powerful now. So there's a separate but connected notion of pluggable type checkers, which will allow there's already a checker framework which has many type checkers plugged into it that will allow checking for all of the things that I've listed there, and for many more. And of course you can now write your own type checker. So static analysis will become a much bigger event in the Java scene. If you're interested in this, I strongly recommend you to go to Alexander Ilyan's talk. Okay, so that's the second of the two medium impact changes that I wanted to talk about. And the third one is the big picture. So I was looking for a big picture, and I found this one. So this picture here, which I've probably unfairly attached to my talk, is a picture of Rip Van Winkle awakening from his sleep. So Rip Van Winkle is a story in American folklore. About a farmer in pre-revolutionary America who goes up into the hills and he meets some odd people and has a drink with them and goes to sleep. And when he wakes up again, his gun has gone rusty and his beard is long and white. And when he comes back into his village, nobody recognizes him because he's been asleep for 20 years. And they say, "Who are you?" And he says, "I'm Rip Van Winkle." And they say, "No, you aren't." They say, "This guy over here, this one, he's Rip Van Winkle." You see, he's saying, "No, that's an imposter. This is Rip Van Winkle Jr., who was a baby when he went away and has now grown up to be him." So my picture, the reason I thought this might be appropriate is because of all the complaints that we get about how Java has been asleep all this time while every other language under the sun has been acquiring closures. So quite unfairly, I thought I should attach some labels to these. So there's Java having woken up after the sleep of 20 years, and there's Ruby and closure, and of course the one that is his son, the imposter, the pretend Rip Van Winkle is, of course, where's it gone? Scala. So and of course one of the features of this story is that he gets himself in a lot of trouble with the villagers by swearing his loyalty to the English king. Now, something has happened while he's been asleep. Did we get that? No? There it is. Oh, bugger. Okay, so something happened. The flag had changed. What changed? Well, between 1770 and 1790, that changed. So what happened when Java went to sleep was, well, that was the situation. That's a Pentium processor, not a Pentium Pro. 1994, 3.3 million transistors. By 2012, when we woke up again to see what was going on, we found that we had this is a third generation Intel Core processor, 1.4 billion transistors. So it's roughly a factor of 1,000 more. And here's the really key thing, of course, that we've got four cores. That's not news to anybody. We all know about this, but it's a matter really of kind of taking it on board properly. And probably I know I'm being unfair really to Java. In fact, maybe thinking about this again, I thought, well, actually, maybe I should be the guy with the long white beard, because we could have seen this coming, and I feel like I should have seen it coming. So here is a document. It's called that describes the P6 architecture. So it's got in it things that you will recognize if you've looked into, if you've understood the Java memory model at all and what it protects you from. It's got things like out-of-order execution. It's got things like speculative execution here. This document is telling us that what the processor is executing no longer corresponds to our source code. So this is I actually recommend you to read this if like me, you've been really a long way behind the curve. This is called the P6 architecture, background information for developers. And came out in 1995. Right. So maybe it was me asleep, because I certainly didn't notice that then. So was Java really asleep? Well, actually, no, it wasn't. The language hasn't changed, and we certainly didn't have closures, but a lot of stuff did happen. So, I mean, particularly Java 5 in 2004 introduced the Java memory model, fixed the Java memory model, got it right, and introduced a raft of concurrency libraries which are fantastically useful and very, very well written. So it's not like the VM or the library developers were asleep. They certainly weren't. The language didn't change, but they were there. So what's the problem then? They provided us with all these high-level abstractions, the new and better locks, the blocking queues, the atomic variables, and so on. These things are designed to protect us from the difficulties of concurrent programming with out-of-order execution and speculative execution and multiple cores and so on. So why can't we just use those and get away with it? Well, the problem is that we can't always rely on those. And when we can't, we just have to make sure that we use adequate synchronization. If you use adequate synchronization, the Java memory model will safeguard you from these horrible things. But if you don't use adequate synchronization, you'll get race conditions, you'll get data visibility problems, you'll get early writes, you'll get word tearing. An unsynchronized program is just a nest of concurrency bugs. And of course they're very difficult because they're transitory, they are non-reproducible, and they will turn up on Christmas Eve when your system is under heavy loading and you want to be away on holiday. And they will turn up when you provide new when you introduce a new version of Java, or you upgrade your hardware, or whatever. This is really the kinds of bugs that we don't want. So why is it so? Why then don't we just? My question is, why don't we just do synchronization right? What's the problem? So that's my answer. Actually, in case you didn't notice it, that's my answer. That's a joke, right? Getting synchronization right isn't impossible, but is really difficult. Why is it so hard to be able to program concurrently with the model that we have at the moment? Well, I couldn't resist putting this slide in as well. Because this is the first computer I ever met. I don't really want to talk about it, and I didn't even program on it. But the thing that I just want you to notice here are these little switches here, these touch switches. You used to be able to use these to input instructions and data, obviously in binary form, and then you press one of these switches to put them into a register. So programming used to be really hard, and writing machine code, and I actually did do that, writing machine code on the bare metal requires you to remember a lot of stuff. You've got to know a lot. You've got to know about exactly where your data is, exactly where your instructions are. You've got to remember which registers have been allocated. You have to hold a lot of stuff in your mind. You've got to remember the opcodes and so on. So the progress of programming has been that we've been allowed not to know things. There's been a lot of progress. We've been able to forget a lot of stuff. When assemblers came in, we could forget what the opcodes were. When linkers came in, we could forget about absolute data location. Programmers' lives have been getting easier and easier. Compilers let us forget about register allocation, stack management. Virtual memory let us forget about paging. Garbage collectors let us forget about memory management. Whoa, that was a big one. Basically, progress is being allowed to forget things. That suits me very well, to be honest, because at my time in life, there's one thing I'm really good at. It's making progress in that way. So what's the problem about parallelism? Why is it that we find it so hard to forget about parallelism? We want to abstract away from that, and we don't want to have to think about it anymore. So the reason why it's so hard to forget about parallelism is that we keep on writing code like this. And this is I chose the most innocuous piece of code that I could think of, which was just the idea is simply to add up all the elements of an array. It's an array of ints, and we're just simply iterating over it. It's the kind of stuff that you might write any day. So what's the problem with this? Well, if you get a picture of it, then my picture of it looks like this. So here's the sum variable, and I want to add in the first element of the array, and then the second element of the array, and then the third element of the array, and then the fourth element, and so on, and so on, and so on. Right? So each one of those elements has to be added in, and each one of them, while it's being added in, will alter the value of the sum variable. And you know what's coming here. You have a choice. You can either apply mutual exclusion to safeguard, to make each one of those addition operations atomic, or you can not do it. If you don't do it, then the operations will interfere with one another and the result will be corrupt. And if you do it, then effectively you're serializing the operation. You're going to lose all the advantage of having those multiple cores. Maybe I should have said something else about those cores. It's 4 now, but it's going to be a lot more soon. It's going to be 8, and then it's going to be 16, and then we're going to have 64 cores on each one of our desktop processors. So this model of how we do stuff is going to have to change. How should it change? Well, the answer is we need to think about divide and conquer algorithms instead of these accumulator algorithms. So divide and conquer it's a really simple idea. I've called it recursive decomposition here because I like long words. But the notion is if you want to add up the elements of an array, then the way to do it is to split it into 2. Add up the elements of the low half, add up the elements of the high half, and add them together, right? And there's no mutability required here. There's no problem of mutual exclusion. There's no problem of contention. So this is really cool. How do you do the left half? Well, you do the same thing again, and you keep on breaking it down like this until you get to a small enough data sample that makes sense to do. So I've called it easier in the title of this slide, but I've put the easier in inverted commas because actually this stuff, although when you get your brain into the right frame of mind, this stuff is very elegant and very nice, and you kind of you sort of get the feel of it. But to be honest, it's not. For people with an imperative background used to accumulator-style algorithms, it isn't really very easy. So I got a lot of the ideas of this talk from watching a talk that Guy Steele gave at the Strange Loop conference a couple of years ago, and I'd recommend you to go and take a look at that. It's on the QCon website. But this is the point at which I diverge from him, and the point at which the key idea of this talk is coming up, because he then goes ahead and he says, well, let's build such a recursive decomposition algorithm for a fairly small problem that he's got, which is splitting a string into words. And what he gets is this really nice, very, very elegant algorithm. It's really sweet, and he shows how it's derived step by step. And at the end of it, you think, yeah, that's really good. And you also think, I don't believe that we're ready to do that on a large scale yet. I mean, we as Java programmers. Maybe I as a Java programmer. We're not all Guy Steele. So the key point of this talk is that we don't have to do that. We can instead let the library writers do it. So the library writers, they are smart guys. They're maybe not Guy Steele, but they are very individually, but they are very smart guys. They know the recursive structure of their data, so they can build algorithms like the one I showed you on the previous page for any given operation that you want to do. I mean, in this case, we're talking about addition, but it might be some other operation. If they know the recursive structure of an array list, and they know the recursive structure of the various map implementations and so on and so on, they know how to do this smart stuff. So why aren't they doing it? And the answer to that is, the reason they aren't doing it is because we're forcing them into this mold here. Because what we're doing is, every time we want to process all the elements of a collection, what we're doing is we're getting them one by one from the collection using external iteration and handling them ourselves. So the collection library writers are sitting there drumming their fingers. They're saying, well, we could do all these really smart things, but all we ever get asked to do is to give up our elements one at a time. Now, on the client side, when you get that stuff over, are you really going to, well, you could put it into an array and you could do that clever stuff, but in practice, it doesn't make any sense to give that to the client programmer to do, because you're going to have to do it over and over and over again, and it's quite hard. Typically it involves interfacing with a fork join pool or some similar thing, so that you can actually split up your task and then assign it to separate threads. It's clearly library work, it's not client work. So how can we let the library writers do it? Well, the answer is we've got to get away from external iteration. So this pattern that there is here has been fine for us for a long time, but it doesn't suit parallel programming. Internal iteration lets the collection choose its own iteration strategy. It could be parallel, it could be serial, it could be out of order, it could be lazy, it could have strategies that we don't know about yet. Instead of writing that, I've used a for each loop there, but it's the same thing, it gets an iterator. We're going to write this. So what we're going to do is we're going to give a behavior to a method of the collection, and we're going to say apply this behavior to every element of the collection in turn, or in whatever order you choose. You can do it parallel, you can do it serial. You just do what makes sense to you, because you know all about your elements and you know a lot about the pragmatics of the system that you're running on. So the key here is this shaded part, the part that I put in dark there, and you'll probably recognize that as a lambda. And you can think of it as a behavior. Well, you can think of it as an abbreviation for a method. But it's a behavior, and we're passing a behavior in to this method, and we're saying, do this for everything. And it turns out that this abstraction is really useful not only for collections, but it's going to benefit all the APIs. So this is like the key point, and the reason I wanted to talk this way was that sometimes it's kind of hard to look at a little bit of syntax like that and see where's this coming from. Right? What's that syntax about? And why is everybody getting so excited about stripping away some of the boilerplate from anonymous inner classes? That's certainly what I thought when I first came across it. So just to wind up now, because that's kind of made a lot of the points that I want to make. You might have detected I couldn't leave it like this, because I felt like saying, well, you know, that for each is very nice in the sense that it's internal iteration, but it's not going to help that contention problem that I talked about a moment ago. You couldn't say, people often say to themselves, well, in that case, why can't I just have a variable outside of there, and I can just say I arrow sum equals sum plus I. And yes, you can do that, but of course that's just going to take you back to the contention problem. Right? So what would you do instead? Well, you'd summing an integer list. You would do by recursive decomposition. But what's the operation that's going to be used? Well, the operation is going to be, you have to define how it's going to build the recursive decomposition algorithm, and how the library is going to do that. And to do that, well, you just need to specify that this is how we're going to build it up. And you can see a tree growing out. You can see a tree growing down there where we add these things together. And the library will take the specification of that operation, and it will turn it into a recursive decomposition. So our job now is just to define that basic operation, and that's what it looks like. The stuff in red. So everyone's heard of reduce, I guess, and maybe this kind of fits in a little bit about what it's going to be used for. And it says basically all we're saying here is take two elements, and the result is adding them together. The result is the result of arithmetically adding them together. And there's just only one really serious proviso I've got to put on that. And I've got to say that operation has to be associative. And I couldn't resist saying that, because people often think associative. You know, oh, I remember associative. It was something I learned in maths. Associative means that if we're going to allow the implementation to do this stuff in parallel and out of order and all that, then the picture that you've got there has to give the same result as the picture like that. In other words, it doesn't matter what order in which I do these things. It doesn't matter how I group them, I should say, as I'm building up the result. And that takes me very nearly to the end of the story. There's only one thing. It's actually quite a big thing. I couldn't really leave it out completely. And that was just to say, well, what's this actually mean when it comes to programming? Well, obviously it means we're going to have to think about lambdas. We're going to have to know how to write lambdas. And I recommend, if you want a bit more technical detail, come to my talk this afternoon where I'm going to cover this. I'm going to cover it in some more detail. But also, what are going to be the data structures we're going to work on? Well, reduction as above, a reduction that I showed you before, produces a single value. But quite often what we're going to be doing is we're going to have operations that are going to change every element of a collection in some way, and then we're going to want to do some more work on them. So we're going to produce a collection. We would like to update it in place. Except I've just explained in detail why we shouldn't update collections in place. We mustn't do that. So multiple successive operations on collections are going to produce this sort of structure, where we get a collection, we put it through an operation, we produce another collection, and we put that through an operation, we produce another collection, and so on. And that's pretty horrible. I mean, there are big disadvantages about this. It requires a lot of intermediate storage, and it's very difficult for the compiler to optimize, and basically it's not a great idea. So a better idea is going to be streams, the new face of the Java Collections API. And just as a taster for my talk this afternoon, I took this is a slide with which I start the talk off this afternoon. There's a piece of code, just a fairly random piece of code from a project of my own. And I then chose the project of my own because I wanted to be rude about it. And then I rewrote it using streams. And I think when you look at this, you can see that we've got a style of API here, which is going to be much more, much closer to the developer's intention. We're taking something here, a collection here. A map operation will transform the value to something else. Then we're going to take those transformed values and we're going to filter them over this condition, and then we're going to find the first one of them. And you can see at a glance about that. In a way that first slide you would have to study in some detail. So we're going to get more readable programs, and we're going to get them with a big bonus of parallel execution, in some cases, not always, but in some cases, coming in for free. Isn't that cool? And we get all of that from Lambdas. So that's it. Now my conclusion is that the platform has been progressing nicely all the time. Actually, the language effort is building up again now after quite a long hiatus. I mean, I'm only a spectator on the outside, but it's pretty clear that things went quite badly off the rails for a few years back then. But now, with Lambdas, I think the Lambda effort is being really well managed, and I think that on the whole, the facilities, the features we're getting are going to be really great. And we're heading towards, there's a push towards a style of functional programming, which is going to have big advantages. And later on, with Java 9, maybe Java something, we'll get reification of generics, which will actually allow us to get a unified type system and iron out those horrible primitives, and we'll get function types, which people have complained about Lambdas not really being. And I think the future for the language actually looks pretty good. So it's going to be a much better, much nicer language to work in, and it's going to adapt itself. Our programs are going to adapt very easily to working on modern hardware platforms. And what more can you ask for? Thank you very much. Thank you.